A couple years ago I finally got my first plants, but as the summer was nearing I started to worry. My housemates weren't home in the holidays and I don't really have neighbors, so who was gonna take care of my plants while I was away? As an engineer I naturally thought, let's make a machine for this. So I built a big watering system using some small pumps, 3D prints and a lot of tubes. But while this idea had potential, it failed while I was away on holiday, so a friend of mine had to save my plants. It also took up a lot of desk space and I did not like all the tubes going to my plants. So then I decided to build a robot arm to water my plants. It doesn't have to take up desk space, it's easy to add new plants to the system and most importantly, it's super cool. My name is Matthias and in this video I'm gonna show you how I designed and built this robot arm. Let's roll the intro. Let's look at the mechanics. I wanted the arm to be able to reach plants anywhere on the windowsill and on my desk. For that, the robot arm needs to be able to span 1.6 meters horizontally. Also, I wanted the robot arm to be able to reach plants close to it, and combined with the ceiling height, that was a bit of a challenge. I decided on using 2 moving arms for the span and 1 fixed arm that can only rotate, like shown here. This way, the robot can move in all 3 dimensions. I decided to use an extension arm as well, which is retracted for plants close to the arm and extended for big distances. For the arms I used 25mm square aluminium profiles. I designed connecting pieces in Fusion 360 and I used my trusty Ender 3 3D printer to print those. I used M6 bearings and screws for the rotational axis and M4 screws and bolts to connect the printed parts to the arms. I wanted to use NEMA 70 stepper motors to move the arms, because well, I had them laying around. However, just slapping a stepper motor on one of the axes is not enough, since the arms will become quite heavy and especially for bigger spans a lot of torque is needed. For every axis I designed a torque reduction system. For the first rotational axis, which I've called delta, I simply used a GT2 timing belt with 2 different pulleys. This gears down the rotation with a factor of 1 to 3.75. I used a piece of wood to mount the motor and the bottom of the robot arm to. On the top of the rotating arm, I used some leftover aluminium pieces with some brackets to create a wall mount for the arm. For the second rotation, which I call alpha, I used a belt which connects to the end of the first moving arm on one side and goes over the top of the non-moving rotating arm towards a sliding carriage. I also added a counterweight here to help the stepper motor. By moving the slider up or down, we can change the angle alpha. And to do this, I once again used a belt, which loops around the arm. On the top there is a pulley and on the bottom the stepper motor is mounted. This design reduces the amount of torque needed by the stepper motor tremendously, although we do need some mat now to convert the amount of steps into angles and vice versa. I'm not going into any of the mat needed for the kinematics in this video, but if you are interested in that, please leave a comment as I am considering making a video about kinematics with position and real-world velocity control. For the last rotation, which I call beta, I first tried a belted design and then a geared design. Both of these were not able to provide enough torque, so I once again used a sliding carriage, this time around the first moving arm. This slider now connects to a length of thread, which connects to a fixed point on the second moving arm. This configuration really helps to counteract the effects of gravity. You see, the bigger the angle, the more gravity wants to rotate the arm back. But at the same time, the bigger the angle, the more the thread is perpendicular to gravity. This results in the motor experiencing the highest gravitational force at 45 degrees, where the force is still reduced by 65%. Now let's look into the coolest arm, which is the extension arm. The extension arm is a smaller 20mm square profile, which fits inside the 25mm square arm. I simply used the belted design once again and fixed the belt to the extension arm. The stepper motor is mounted on the other side of the arm and also acts as a bit of a counterweight. With this mechanical design, the friction in the system can hold the robot arm in place without power at a lot of extreme angles. So if there is a power outage while you are watering, the robot arm doesn't necessarily crush all your plants. Now the stepper motor should be able to move the end of the robot arm to any plant, but we also need to get water there. For this I used a lot of tubing, which I reused for my previous watering system, and I used a 12-volt water pump. I used a 13-liter plastic box as a reservoir, which I put in another box for safety reasons. With this reservoir, the robot arm should have enough water for 3 weeks in the summer with my plants. Now that we've covered the mechanics, let's take a look at the electronics I used. First of all, we need power. I used a 12V 8.5A power supply that I had laying around for the motors. I added a buck converter to step the 12V down to 5V for the controller electronics. I used an ESP32 as the heart of the system. It has 2 cores, lots of speed and memory, quite some pins and Wi-Fi. To control the stepper motors, I normally would have used a cheap stepper driver like an A4988, but this time I chose to go a bit fancier with TMC 2209s. In order to see what the robot arm is doing when I'm away, I used an ESP cam, which is mounted to the second moving arm with a printed bracket. This ESP is powered with 5V, which is stepped down to 3.3V with the onboard logic converter. I was experiencing low FPS on the ESP cam, so I added some capacitors to smoothen the supply voltage, and I tried adding some tape in the neighborhood of the antenna, as recommended by the internet, since the onboard PCB antenna is pretty shitty. I'm not sure if this helped a lot. In the end, I used an old router in my room to connect the ESP to, instead of using the one downstairs in the house. This boosted the FPS to workable levels of around 3 to 4 frames per second. Okay enough. Since the ESP cam uses quite some power, I added a MOSFET to the main controller board, which I use to turn off the ESP cam when it's not needed. I also used a MOSFET to control the pump and added an SD card reader to save plant information and settings. Since I was running out of I/O pins, I added a 74HC595 output shift register to connect some debug LEDs to. I then used the lesser known but just as useful opposite of the 595, the 74HC165 input shift register to connect the homing switches to. These homing switches are needed for the controller to know where the robot arm is, so it can control the position and doesn't just bump into things. The controller moves the motors until the switches are clicked. Then the controller knows where all the motors are and can track the position and angles of the robot from that point. When I was done prototyping, I soldered all the components to some perf board and started eating ice. I needed a simple enclosure. And with that done, it was time for some coding. I'll quickly explain the general structure of the code, so you get an idea of how you can split up the big task of watering plants with a robot arm into smaller steps. I basically just used a whole lot of classes, which if you really don't know, they're like collections of code with variables and functions, and you can treat them like variables too. First, let's look at controlling a single stepper motor. I made a class called DOF, Degree of Freedom, which inherits from the Excel stepper library. This means, explained very simply, it uses this Excel stepper code, which controls acceleration, as the basis, and then adds the code of the class. This way I could add support for homing. The TMCDOF now inherits from this class and adds current settings and communication with the stepper driver. Now we can control individual stepper motors, and because we are using classes, we can easily reuse this code for all the stepper motors. To control the stepper motors together, I made the Stepper Manager class. This class can move stepper motors at the same time, home the entire robot arm and control the power of all the motors at once. However, the Stepper Manager is quite dumb. It doesn't understand robot kinematics, so if it needs to convert angles to steps or vice versa, it asks its friend, the Coordinate Manager, for help. Now we can really move the robot arm to where we want. To control the pump, I made a Water Manager, and to manage the Wi-Fi connection, I made a Connector class. I also made classes for the shift registers and the camera. I made one other class, the Plant Manager. This class is like the final boss. It gets plants from the SD card, can remove and add plants, keeps positions for plants, and most importantly, it can water plants, as it can access the Stepper Manager and the Water Manager. Now I could talk a lot more about this, but then this video would take hours, so let's move on to the app.
There's an app?
Yes, there is. I made one myself using Android Studio and a whole lot of patience. The app connects to the IP address of my robot arm and uses TCP and JSON messages to communicate commands. It features a plant list, a page for moving the robot arm, a page with general commands and of course a page where you can watch the robot arm as it waters the plants. Here you can also see another camera. I added a simple webcam with an old laptop, which streams its feed over the internet, so I don't have to rely on one shitty camera, but instead I have two shitty cameras. Okay, it's time to put it all to the test. Let's open the app and water my plants. Let's click on Water Scheduled Plants. So now we can go to the camera page, where we have to give permission for homing. All the big steps in this process, like moving and watering, need permission, so if anything goes wrong while you're on holiday, the robot arm doesn't keep going and destroy all your plants. While the robot arm is homing, let me explain the watering schedule. So for every plant you have to define how many times per week it should get water and what amount. If the plant needs water once per week, it will get water on Tuesday. If it needs water twice, it will also get water on Friday, and if it needs water 3 times, Sunday is the next day. So now the homing is done and I have to give moving permission. Now the robot moves to the closest plant on the windowsill. You can see it first moves delta, then alpha and beta, and then it will move the extension. This way we can reach all plants safely. The robot has arrived and now we just need to give permission again to enable the pump. There we go! The amount of water the plant needs is converted into the time the pump needs to stay on, and after that time the pump turns off. Now we can move the extension arm back and move to the next plant on the windowsill. This process repeats for all the plants on the windowsill that need water. For the plants on my desk, the robot arm just moves to individual plants and then back, since the robot is not yet smart enough to avoid colliding into other plants. As for my spanning requirement, the robot arm can reach plants everywhere on the windowsill and can span up to around 1.7 meters. Well, that's how far I am now. I've already used this robot arm while I was away on holiday, but unfortunately it did fail after 1 week. However, it was easily repairable and the robot arm has been watering my plants successfully for the last couple of weeks, while I was not at home most of the time. So I'm very happy with the arm so far, especially considering that I built it for less than 200 euros by my estimate. Now I'm not done with this project anytime soon, as I'm planning a lot of upgrades to this robot arm, like reducing backlash and improving the camera system. I'd also like to add some motors to control the end effector rotation, since some plants are really hard to reach at this moment. And with such a big robot arm, there's so much more that this thing can do, besides watering plants. If you're interested in any of that, don't forget to subscribe, and if you like this video, please give it a thumbs up. Thanks for watching, I'm Matthias, this is Methanication, and don't forget to water your plants.